thank you for being here, and I also thank our guest, Rémi Ronfard from the Grenoble, and he's an expert with long experience in computer graphics, 3D modeling and animation, and procedural animation in particular. And he's been into research for a long time, both in research companies and in the academia. And he's now the director of a team called IMAGINA, which stands for
Intuitive Modeling
and
Animation
Okay.
for Interactive Graphics and Narrative Environments.
One peculiarity of his research is that it combines these technologies, 3D technologies and animation with a narrative content. Okay.
Sometimes.
So, some narrative content. Okay, so thank you.
Thank you, Rosanna. Thank you for the invitation. Thank you for coming to my talk. So I'm going to start with some motivation and context to explain to you that in recent years, for the last 10 years, I've been interested in how to use computers to make movies, and especially animation movies, computer graphics movies, but also movies. And right now, movie making, it can be done on a computer, digitally, from start to finish. Everything is digital. You type the script on a computer, you draw the storyboard on a computer, you can even have a virtual stage where you direct virtual actors on a computer, and you edit with software on a computer. On the other hand, it's very strange that those steps are still very separate from each other, because this is text, digital text, this is digital pictures, still pictures, this is digital animation, this is digital video, and there's very little way to translate from one step to the next. So it's still a very long process to go from script to storyboard to stage and editing. And one motivation for the work we are doing comes from something Alfred Hitchcock said 50 years ago, where he was speaking with François Truffaut in the collection of interviews, and he was saying, wouldn't it be nice if there was a computer where we could put the screenplay at one end and the film would emerge at the other end, complete and in color. And he was thinking at the time, IBM was building supercomputers, that IBM could build a machine like that. So it's interesting to reflect 50 years after, how far are we into making movies by computer in this fashion, going from the screenplay. And it turns out, in some sense, a video game is a little bit like that, right? It starts from a screenplay and it produces a movie almost in real time. So you get a sense that the technology now makes it possible to generate movies by computer. On the other hand, there is still a lot of work that's required in order to do that. So one motivation when I started working on this, it was not at my university in Grenoble, but in Montreal, in Canada, with a startup company called Extra Normal Technologies. It was created more than 10 years ago, and their mission statement was to make 3D animation for digital storytelling, making it as easy as possible to create movies from script. And the motto was, if you can write a script, you can make movies. So it's a little bit like the Ratatouille motto. And the technology was called text to movie, so it's an elaboration on text to speech. So you have text to speech and you have text to animation, and then you get text to movie. It was shut down in 2013, but it was reborn in 2015.
Hi, my name is John, and I'd like to tell you how incredibly easy it is to make your own animated videos using Normal Make. All you have to do is choose where you want the scene to take place, choose one or more actors, type the dialogue you want performed, use our text-to-speech voices, or use your own sound file. Press play, and you have made a movie. Normal's movie-making artificial intelligence takes care of the rest. All of my performance, the lip sync, my actions, and the camera cuts happen automatically. The only input that is required is the text I've just spoken. So really, anyone and everyone can make a video. 3 minutes of your time to create 30 seconds of video. And research shows that the majority of people prefer watching videos to reading text. So why don't you turn your text into a movie? And you can do it right now at normal.com.
Okay. So you can get the feeling of what they are doing. It's not, they don't produce Hitchcock movies or anything complex. They're short movies of a couple of minutes, but it takes a couple of minutes to produce them, which is very interesting. But it also raises scientific challenges. The first one is natural language and story understanding, because you need to analyze a script. It's initially written in natural language, and you have to get the computer to make sense of it. So that's a very difficult area, probably the most challenging of all. Story understanding has been part of computer science for a long time, and progress is very slow. It's very challenging. Next, you have behavior-based 3D animation. If you recognize actions mentioned in the story, how do you animate them? So you need very high-level 3D animation for directing virtual actors. And then you have virtual cinematography for placing lights and cameras automatically and editing them. So film editing is also important, to a single string of film. And so if I continue motivation, in my team at IMAGINA, we are interested in natural interfaces for designing shapes, motion, and stories. So we are revisiting this research program a little bit. We are not trying to do automatic generation of movies, but try to have interactive narrative environments where the user is the director. So you're the director, and the system has all the required skills for placing cameras, doing film editing, generating animations, and you are in the position of the director, right? Which is not the case with current systems. So that requires an explicit representation of story goals, character actions, events, causal relations. Since we don't work in natural language processing, we usually label them ourselves, and it requires a directable film crew of virtual actors, virtual cameramen, virtual lighting technicians. And in my talk today, I will speak mostly of virtual cameraman and a virtual film editor. How do we get a computer to act? So I'm going to speak of three topics. One is a language for directing virtual cameras called the prose storyboard language. Then in the second part, I speak of our model for performing continuity style video editing, and a very short section on ongoing work in progress in story-driven animation. So the prose storyboard language is pretty much something I'm working on, I've worked on for the last 10 years, and it's still continuing. So the motivation is that we would like to learn cinematography from examples, annotating examples, and have a language for scoring the cinematography, writing it like music. So cinematography is writing with motion, but there is no shorthand notation to choose shot compositions. So the prose storyboard is trying to be such a shorthand notation, something that you could use to direct a camera and to tell the computer what kind of shot composition you want to achieve. So one important thing with the prose storyboard language is that shots are sentences, they are not words. So in film studies there has been a lot of debate whether film was a language, and if film was a language, what was the vocabulary? And people are trying to say shots are the words of that language. But it doesn't work very well, because shots can be as complex as you want them to be. Rope by Hitchcock is a movie with a single shot, but that shot makes up the entire movie. So in the prose storyboard language, shots are sentences, and the words are the frame compositions, the different way that you can compose the frame, and actions of the actors and the cameras. If I look at the state of the art, much work in virtual cinematography, in fact, deals with very simple shot composition. Shots with one character, two characters, even extra normal and normal is mostly limited to those very simple shots. There's little work on shots with 3 or more actors on screen. And there's also little agreement between researchers in film studies on how to describe complex shots, both in time and in space. So how do you describe this? What would be the denomination for a shot like this or a shot like that? How would we describe this or that? So some cases are easy, some cases are harder. If you look at Citizen Kane with a very large depth of field, you have a shot that's quite difficult to describe as well. And how would you describe this? You know this shot? The opening shot from Tao Gold by Orson Welles, right? So pay attention, it's not very long. I don't think we get sound, but it's not so important, it's mostly visual. Okay, somebody's putting a bomb down, and the movie starts like this. And the camera moves a lot. Oh, we do have some. So it's mostly an illustration of how complex a single shot can be. I'm not saying we can generate shots of this complexity, but ideally, right?
Automatic wells.
Why limit ourselves to static shots?
By the way, just as an annotation, there was a very precise script concerning sound for this opening scene, which has been cut by the producer.
The description
Of sound. Completely. Including all the sound, music.
Well, that would be interesting because that's one of the future work we want to do is to include sound in shot this, but we don't. So now we are framing the two main characters, and it's becoming obvious that they are the main characters, although they have different scope. And you see the composition changes very frequently, but
you folks
these shots are well composed.
I am, yes.
Where were you born, miss?
Mrs.
What?
It's like a short movie.
Name is Vargas. Hey, Jim! You see who's here?
How is it called
Sure,
in
Mr. Vargas.
L'infernale
Out on the trail of
Quella.
another dope ring?
L'infernale
On the
Quella.
trail of a chocolate soda.
L'infernale
My
Quella,
wife.
l'infernale.
No, I mean, in French it's a plan séquence. So it's
Piano
going behind a shot of the
sequenza.
sequence. Piano sequence.
Only one of them. The Grandies are a big family. Good night. No purchases, Mr. Lineker.
Hey, I got this.
You're American citizen, miss?
I got this ticking noise.
Yeah, okay.
No, really, this
Good
ticking noise in my head.
Again, moving to another
I
composition.
realize this is the very first time we've been together in my country.
Do you realize I haven't kissed you over an hour?
That resolved the sequence. So you see, it's so the idea with the prose storyboard language is to think that
È bello.
a shot like this, it's in fact a sequence of shot compositions, and it's important to know what are the actions that go from one shot composition to another. So that's the basic idea we've followed. Is that the prose storyboard language should be intuitive, human readable, so people should be able to write or read it. Should be compact, expressive, so simple cases should be simply described, but it should also be as complex as needed, so it could be used to notate all movies. And it should be a notation in the sense that it should be machine readable, compiled, executed, so if you type a short composition, the computer should be able to understand it. So here is an example to give you an idea. So this time it's taken from a scene from the movie Back to the Future. So I'm showing 2 frames of that shot. It's what I call a composite shot. It starts with a transition, which is a cut. And then, so there's a transition, it starts with a cut. Then there's a first composition, it's shown here. and it's a medium close-up on 3 characters, M, S, and G. Then, so here the temporal cue is done just then, so after a while, there's a reframe action because the camera makes a dolly movement to the right that creates a new composition. And here you have a medium close-up on, again, the same 3 characters, but just to give you a rough idea of the way it works. So a shot is a sequence of compositions and cues. And the cue determines when camera action change the composition. So that's the basic idea. So the references I used are from a book by Thompson, Grammar of the Shot, because I had to make a choice. There are so many books. This one is a tutorial. And also the inspiration for the name, Prose Storyboard Language, comes from the book by Proferes, who teaches film at Columbia University, and he uses the idea of writing storyboards rather than drawing it, because he says not all directors can sketch or draw very, very well, but they can all write. So you can write every shot, the description of every shot of a movie. From the work on the movie script markup language, which is some representation for the structure of a movie into scenes, but it doesn't go to the level of detail of the shot, so it is complementary. So there are 3 types of shots according to Thompson and in the storyboard language. The simple shot is one when the camera does not move or rotate or zoom. It's like the Lumière brothers movies. You put the camera somewhere and actors move in front of the camera as if they were moving on a stage. So the frame composition changes only when actors move in the frame. So in that case, we have a frame composition, and then we give the actor movement. Then there is the complex shot, where the camera does not move, but it can rotate and zoom in and out. Then you have camera pan, tilt, and zoom, which are the 3 actions, or again camera movement, and they can happen together. So the prose storyboard notation in that case is the frame composition and the actor movements and the camera rotation actions. And then the composite shot is one where the camera and the actors move freely, like in the Touch of Evil example, the Orson Welles example. Then the frame composition changes more dramatically due to actors in the frame, camera motion, or both. And the prose storyboard notation in that case is frame composition, actor movement and camera movement, leading to new frame composition. I don't want to go into the detail of the language, just to show you that it can be parsed by a computer, so it has a very rigid syntax. It can check that the syntax is valid for you, things like that. Elements of frame composition in the prose storyboard languages are relative to the camera, so we describe the shots as if we're watching the movies. We are not describing the shot in terms of where actors and cameras are on the set. We are describing where they are from the point of view of the camera, which seems to me to be very important, because that's what is important. So elements are the size of each of the actor, from full shot to close-up. So we had to make a choice. Not all books agree on this denomination, but it's useful. So I used the one by Barry Salt in his book Moving into Pictures. I used that example as a reference. Then the profile angle for each of the characters. Where are they facing relative to the camera? Are they looking direct to the camera, front, or left to the left-hand side of the screen? So we have 8 basic positions. And where are they on the screen? So screen position, especially the horizontal position. Are they on the left side of the screen or the right side of the screen? So if we look at the notation, here we would say that it's a low-angle shot because the camera is under the character. A big close-up of a girl who's looking 3/4 left, and she's positioned screen center. So I try to fit all those elements of description into a single sentence, in the hope that it remains readable and understandable to a human. So in that case, we would say it's a medium close-up of Marianne. We could add, she's looking towards us front, and she's screen center, but it can be omitted because that's a default value. And there's a big close-up on the scissors in the foreground. And we need to add that to make it explicit. So some people mentioned that I should also say there are two pictures on the wall. They are part of the shot composition. Right now I'm focusing on the actors rather than the object. So here the description would be a medium shot. So usually in the post-storyboard language we read from left to right. So it's a medium shot of the girl. She's looking 3/4 back right, and she's on screen left. And Ferdinand, who is front screen right. No, not quite. But generated 3D animation. But we have placed the cameras and the lights and generated some brushes. And now we want to edit those brushes into a movie. So the situation is like in television where you have multiple cameras and you want to edit a movie from those many cameras. So it's like a multi-camera production. Right? So they're all synchronized together, and we want to find what would be the best editing automatically. And actually, extra normal works pretty much in the same way. When you type, you create a sequence, it is first recorded by multiple cameras, and then there is a similar algorithm that chooses when to cut and when to cut. So this is a case where we have built a 3D version of a movie scene. So the movie scene is from Back to the Future, and we asked the computer artist to recreate that scene, to create the set, to create the characters, their costumes, and their movements. They placed the camera exactly as in the movie, so we have more or less recreated manually a scene from Back to the Future in order to test. Okay, so what are the problems that we face when we try to edit a movie? Well, there are many errors that you can do if you're not a professional film editor. There are continuity errors, like you get the left to right ordering of the characters wrong and you confuse the audience. You create jump cuts that further confuse the audience. You get the screen position or the gaze directions in inconsistent ways. A film editor knows how to avoid those mistakes. So we've tried to propose an algorithm that avoids those well-known mistakes. Sometimes film editors make those mistakes by design, but we don't do that. We don't do that because it's too risky. Our programs are not intelligent enough to break the rules. So we're trying to prevent them from breaking the rules. We also want to avoid, and that is probably even more difficult, non-motivated shots. So if you show a shot and it's correct, it's well composed, and there's no film editing error, but it does not belong in the story, it's showing something that is not important in the story, you're also confusing the audience. So shots and cuts must be motivated. So our solution is an optimization framework where we try to give a sequence of shots where they are as motivated as possible, with a strong motivation, and avoiding all the continuity errors. So we cast film editing as an optimization problem. So I'm going to explain now. But first, the related work. There has been much work, in fact, in film editing, automatic film editing. It's not a very big research community, but in the last 20 years there have been attempts. The most famous attempt was 20 years ago, the virtual cinematographer, which uses finite state machines. Finite state machines are used a lot in video games to program the behaviors of non-player characters. So the idea in that work was to say the camera is a non-player characters that should react to what the players are doing in the game and what the other actors are doing in the game. And it should work with a finite state machine. So each state in the machine is a camera position and a frame composition. They are organized into a machine where you choose those shot compositions so that they never violate the rules of editing. So there are some sort of idioms that if you alternate between a shot of the tree and a shot of this one, the shot of that one, all those transitions are always possible. So you eliminate all the errors and you build them into a machine where you know you're going to do correct editing no matter what happens. And then you change state according to what is happening, what the actors are doing. So it's a reactive machine. When you go along the timeline, right, when an actor starts an action, it triggers a transition of the machine. It creates a cut to a shot that has been hard-coded. Some programmer has said, okay, every time somebody speaks to somebody else, we switch to a two-shot of them. And if it becomes too long, we switch to a one-shot of the speaker and blah, blah, blah. So it's all encoded. Which works very well, except that it's mechanical. It's mechanical and you can feel it very much in the timing of the shot. It looks like you feel there's a machine doing the cutting after a while, especially when it's repetitive. So that's one of the issues. Another issue is that you have to encode all possible actions. So it works very well in cases like debate, dialogue scenes. You switch from somebody speaking, somebody else speaking. That's easy to encode. But if you have multiple actions in parallel, you have to encode all those idioms and it becomes tricky. So in fact, it was limited to dialogues between two actors and dialogues between three actors. And it's never been very much extended to anything else. So in our case, it does not fit the requirements. We would like to edit complex movies. So after that, more recently, Mark Riddle and his students have proposed an optimization-based approach, which uses dynamic programming, where the idea is that you break down the action again into what they call dramatic beats or actions, that makes sense. And at the beginning of each beat, so it's the beat, B-E-A-T, is taken from Stanislavski, right? And Stanislavski, if from what I've read, meant bit, a bit, like a minimum element of dramatic information. Well, that's the story I read, but it may not be true. But it's classic to decompose the sequence of actions in drama into beats, and here what they propose is to decide which camera should go at the beginning, for each beat. And the advantage is that you have a limited number of decisions to make. Right? Let's say you have 10 cameras and 10 beats. So you only need to evaluate 100 possibilities and you can solve, optimize based on the notion that what's important is how good the camera covers the action and how good is the transition. This is nice, but again, the fact that you change the camera at every change in action appears mechanical and a little bit strange. So some people have called this the dragnet style of movie editing because there was a series, a TV series in the US called Dragnet, where they would film like this. Every time somebody speaks, the camera switches to him. So if they speak faster, the camera cuts faster. If they speak slower, the camera... So it's nice, it works, but it can get annoying. So what we did, and I won't go into all the details, but we proposed a solution where you can make decisions to switch cameras at any point in time rather than at the beginning of it. And the main innovation in that work was to search in a larger space of possible movies, which we associate with semi-Markov chains. I won't go into the detail of semi-Markov chains, but it's a very powerful representation. It means that we model the film editing process by our machine as a process where, so you know where the camera is, you know what is the current action, you decide to cut to a certain camera for a certain duration of time. So we make a decision not just to cut to the next frame, but to cut for a certain duration, a certain amount of time. So we have to look ahead a little bit, and in this fashion it allows us to control the pacing, the timing of the cuts, which previous work has not looked at very much. So currently we show that our system can generate edits of different reasons, but sometimes they are good, sometimes they are bad, but at least we can control that. So I will illustrate the kind of mistakes that we try to avoid, to penalize. So our cost function is meant to minimize the occurrence of some mistake. So one of them is that we follow, it's something very popular in virtual cinematography, it's the Hitchcock principle. I don't know if you are aware of that. It's very simple, even simplistic, but it's very useful. It says that the size of a character on the screen should be proportional to its narrative importance in the story at that moment. So it sounds a little bit like a joke again. Hitchcock always is, you never know if he's serious or if he's joking. But it's in fact very useful, because if you take it in the other way, if you break this rule and you're showing a character with a very large screen space and he plays no role in the story, you're confusing the audience, right? Now, on the other hand, if you show a character and it's almost difficult to recognize him because he's in the background, and he's the important protagonist at that moment, you're also confusing. So following this rule is in fact a good idea most of the time. So we follow it a lot, right? So we measure the difference between the size of a character on screen and its importance in the story. The importance in the story is difficult to quantify. That's a tricky part of each rules, right?
You say in a specific moment.
Yes, at a specific moment. So to us, it's the number of actions that the character is taking, is where the character is playing a role. But that's not sufficient. Sometimes it doesn't work so well. And we also do that at two time scales. The time scales of the activities happening, so maybe a matter of minutes, and the actions they are performing, so it's a matter of seconds. But it's a rule of thumb. It's not an exact science here. So examples. So then we rank the shots based on action visibility and action proximity. So here you have a case of if this character is speaking, right? There's low action visibility, so it's not a good choice, right? Here, this is a much better choice if we want to, if this is the character speaking. And action proximity, it's the Hitchcock rule, so if the action is here, those three characters speaking together, it's better to have high action proximity most of the time. So that's for choosing, motivating the shots. We try to motivate them by use of the Hitchcock rule. And then, in terms of editing, we try to avoid discontinuities. So it's a model of continuity editing. You don't want the cuts to be noticed by the audience. So screen discontinuity, for instance, here, the Marty character appears to jump from one part of the screen to the next. We discourage that. We prefer to maintain continuity. Here, the Marty character remains on the same side of the screen. It's probably going to work better. Motion discontinuity also we try to avoid. So here, the white character is moving in that direction, but now he appears to be moving in the opposite direction. That's confusing. We prefer to see him moving in the same direction. And here there's a subtle thing that motion discontinuity, so it means same direction, but also it's important that the character is following the path. If he was going back, right? If he was moving in that direction, but on the right side of the screen, it would create what people call, film editors call the hiccup, motion hiccup, that he appears to be performing the same movement on screen as in the previous shot, so as if he was repeating himself. Right? We try to avoid that because you notice that gaze discontinuity we try to avoid. So if the Marty character is looking toward the right in the next shot, you don't want him to be looking to the left. So you also don't want to see this character who is not important in the action, but that's a different topic. That's the Hitchcock rule. You prefer gaze continuity. So there are some examples. So the animation is incomplete. The artists did their best. But it was a progress relative to previous work, because one thing that was a problem in previous work is that there was no facial animation at all. But if you do a close-up on a character that is not animated at all, it looks terrible. So here we try to be as close as possible as we could to good look, to a case where all the shots were equally good. So you can see the actions, the dramatic beats, and you can see the camera choices, and you can see the completed editing. And we did some comparative analysis. So we noticed that our solution, our optimal solution, is quite different from the one in the movie, which is not entirely surprising. I would be surprised if the editor for Back to the Future was only trying to minimize error. I think he had other things in mind at a higher level, like maybe preserving surprise, maintaining attention or interest, things that we currently cannot deal with. But it was interesting to notice that at least the film editor in Back to the Future was not making any of the mistakes we are trying to avoid. Usually they quite agree with that.
Those are the possible choices.
Oh yes, at any given time you can see we have
At any given time,
25 cameras.
Okay, 25
As
cameras
if
each time.
the scene had been filmed by 25
5 cameras and
cameras.
then
Yes. So that's the way it works. And in those 25 cameras, we have the cameras that were actually used in the movie, which we reproduced as much as possible, and some cameras we added to create possibilities. So, to conclude, this is a computational model for film editing that incorporates knowledge about shot composition and film grammar or film editing grammar. It has an efficient offline algorithm. So what that means is that you need to know the entire sequence, it's offline, in order to compute the editing, and it works much better than if you are trying to make decisions online at any given time, which is something I like, because that's one reason why I don't like the state machine approach, is that the state machine, it's like television, you're editing on the fly. But usually the result is not as good. Here we're taking into account the future when we make a decision. And so we're saying this is a framework that's suitable for automatic film making. And of course it has been tested on one sequence, so more work is needed to further evaluate it and see how. Recently, a few weeks ago, we extended showing that we can incorporate other variation, not just the tempo, the tempo of the editing, but also the focus. So if we manually edit the script by deciding to focus on a given character, we can generate variation focusing on each of the 4 characters, for instance, and still produces editings that make sense. But it's hard to evaluate. We also had a paper on evaluation of film editing. It's very difficult. So we looked at how the Oscars, they choose who is the best film editor every year, right? They give an Oscar for the best film editor. So we looked at what are the criteria for best film editing. But there are no criteria. It's just peer evaluation, right? And usually, in the history of the Oscars, they noticed that usually the Oscars for best editing goes with the Oscar for best story, best screenplay. Because the only recognized criterion is that film editing should support the story. So if the story is good, you get the impression that the film editing is good. I don't know, but it's a mystery. How do you evaluate what makes a good versus bad editing? It's a very difficult issue, and a very important issue for us, because when we publish our work, we are always asked to provide an evaluation. But how do we provide an evaluation, since even experts don't believe there are valid criteria? If you ask a film editor, 10 film editors, they have 10 different opinions. If we ask people who don't know about film editing, it's even worse, because they don't even notice sometimes. So evaluation of film editing or frame composition is a tricky issue, interesting issue. And I think more work is required, more collaboration between film studies and computer science, and maybe the fact that we can simulate different versions of a movie could be, we could devise interesting experiments in the future.
Actually, if you take into account editing, well, surely it's your preferred corpus, but on the other side, when you evaluate film editing, there is sound, which is very important, that includes various kind of transitions. So if you strip away sounds, that doesn't mean probably that editing would not have been so good, actually, because while doing the edit of the film, the main editor, together with the director and the sound editor, they are putting together various layers. So actually, you're missing a point that maybe is very important to evaluate the final result of editing.
Yeah. Yes, so that is very true. So you can see all the steps of the computation playing behind me. But to answer the question, so we know when the actors are speaking, and we take that into account, but we don't do anything special with respect to sound. That's true. Also, we work from the actual soundtrack of the movie, so we never change that. Whereas a film editor would have choices, right? Which sound to include into the mix, but we don't have that. But you're right, the connection between sound and image in film editing, it's very difficult to study. It's very interesting, but very difficult to study. Okay. With some sensor in front of cameras so that we can record the movement. And so there is almost no possibility to change that. It's given. In our case also, the animation is given. We can change where the camera is, we can change the editing, but we cannot change the animation because it doesn't look right. So procedural character animation, it's an open research issue, a very active research issue. So here, if I go back to the objectives, generating 3D animation, well, it's hard. So we've tried to do things to make it easier to create animation and to change their styles. I'm only showing one slide, but creating animation by sketching strokes. Right? So here, we're sketching strokes rather than entire 3D configurations. So this has the advantage that a skilled animator can do that in seconds. So it's easy to create all sorts of variation, and it's also a compact representation of the movement that can be changed a little bit. You can make it faster, and it's also in screen coordinates, so it can be expressive. So we are looking at ways to generate those strokes, or to ask for some creatures to follow paths and things like that. Try to describe the motion, the character animation in screen coordinates, just like the storyboard language. But that's a work in progress. We have also looked at directing virtual actors. So we did work with one of my students and with a theater director in Paris, asking two of his students to play a short scene from La Ronde, the Schnitzler play. So it's a dialogue between a man and a woman. We asked them to play it without any expression, which is very difficult to do, in fact, right? Like reading, trying to put zero expression into it, and then to read it with different expressions. So we chose things like what we call dramatic attitudes. So to be seductive throughout the scene, or to be thinking throughout the scene, or to be scandalized throughout the scenes, and things like that. And we tried voluntarily to move away from basic emotions. There's a lot of work and research on generating basic emotions like joy, fear, anger. But for expressive animation, dramatic animation, it's not the most important thing. The most important thing is to show dramatic attitude, meaning how you feel about what you're saying. Do you believe in it, or are you skeptical of what you're saying? Are you asking? So we are looking at ways that you can express, that a virtual actor can express that he's scandalized, and it works. So it's a very difficult. The student actors were more expressive. So we had two versions of it. A more realistic version that didn't look so good to people when we evaluated it, and then we did a cartoon version of it in the hope that it would be more expressive, and we are still working on that, trying to generate at least speech that has the correct dramatic attitude. And this is a work that will continue in the future. And then another way that we are looking at generating animation is by playing and acting. So we're starting a PhD where so one of my students starting to work on the idea that we print figurines of the character and we put some sensors that can record their movements, and then when you're holding the two characters and you're telling a story with those two characters, and the way you move them, you try to express what they are supposed to, what they should express. And then we try to merge the motion, the recording motion of the figurine with the facial expression of the storyteller.
Like puppet theater.
Yes, some sort of puppet theater, virtual puppet theater. So that could be an option for creating, with minimal input, just the motion of a figurine, some more expressive animation, and without doing a full mocap. But that's only one of the